this is like take the differential, right? Differential, and because E is this one, so you will take minus J K. So you can write down minus J K E X equals to minus J omega mu and H Y. Okay, so your E X over H Y will equals to omega mu over K, and this is our wave impedance eta. Okay, and if you change K to omega square root mu epsilon, you can cancel your omega and a square root of a mu out, and eta will equals to square root of mu epsilon. Okay, so you will know the ratio between E and H is the ratio mu and epsilon, your material properties, and take the square root. Okay, those are these two equations are very popular. It's very common for us to use for this eta equals to square root mu epsilon, and the Vp equals to 1 over square root of mu epsilon. How can we use it? We will have more detail, but I will give you the result. The result is, if you see you usually use mu 0, usually, like 99% in your life. Yeah. But if you use epsilon, will equals to epsilon r times epsilon 0. Okay? If this is FR4, you use 4.203. If it is Teflon 2 point something, you will have a table in your appendix. You will check what is your epsilon r is. Then you will have your epsilon here. Then you will know these two equations according to, if you already know the different epsilon r. Alright? This is we usually use it. We use it a lot of time, very commonly, and today I'm trying to review. Actually, we derived this last week. Okay? Okay, now we can start. So far is a review.
So if you have any question, just come to me or you check your book. Now we are in 1.4. We are talking about wave equations. But for those wave equations is only for the lossless case. And actually, lossless case and also this one, we have the dielectric. We have different materials. Mu r is not just only one. Mu r equals to 1 means that's air. If that is 1, there are some materials, okay? And now I will give you more reference. This, for this part, is not in POSA. This is from other books. If we use that, we will have more details about the materials. The key is I try to explain these two equations carefully, not only just epsilon equal epsilon r times epsilon mu equals to mu 0, not only this one, but I try to have more reference to discuss the material, okay? So for the electromagnetic materials, there are many kinds, different materials. If you have the insulator, or you say dielectric, like FR4, or if that is a conductor, you have a PCB, FR4 PCB, you have a conductor on the bottom, in the bottom and on the top, right? There are two conductors. They are different materials. Insulator, dielectric material, and conductors. Okay? There are something between conductor and the insulators. It is a semiconductor. You change your property according to your voltage or current. You can control it. This is semiconductor, right? They are, these three, they are, if we apply the electric field on it, we try to think about what that is. And there are something different. It is, if you apply magnetic fields on it, we would say that it's a magnetic materials. This is different. It's far away from what we are trying to discuss. And there are more different things. The artificial materials, people make it. It's not nature. Okay? So those are the magnetic materials. So this is, yeah, Maxwell equations, right? I always derive it. I write down it every week. We also define our epsilon equals to epsilon prime minus j big epsilon double prime. This is a more accurate epsilon, which has not only your pure number, but also not only real number, but also the imaginary parts. Okay, if you are getting deeper to this field, you will see this very open. And also for the mu, they also have this treatment. Okay, this one is not very hard. This is also common. Our J, as I said, do you remember that I write down there? I said it's important, it's a key. Our J equals to our conductivity times your E field as well. So if this is a conductor, if this is not a conductor, if this is, we are talking about a dielectric part, this is an insulator, sigma equals to 0, you don't have J on it. Just like if you have an insulator, there's no current, right? There's no current on an insulator. But if that is a conductor, it is possible you have current on it. So how to design it is an insulator or it is a conductor? It depends on sigma. Okay, if this one sigma is large enough, it is a conductor. This is conductivity. Okay, if this is 0, it's an insulator. You don't have this term because there's no current. All right. So materials. Okay, also for a conductor, if the conductivity is a large number, it is a high conductivity material. If the conductivity is small, it is a low conductivity material. Just depends on the number of sigma. Okay, metal. So what is metal? The conductor. I copy these materials. I refer to this book. Okay, if you are interested in the materials, you can check the book. So what can the metal do? So for the metal, it is in a microwave, in our field, your metal can be a wire or a guide wave boundary materials. because you have something. You will have current on it. Okay, it's a metal. And also, it is a carrier or structure. It can support, because your circuit cannot just floating in the air. You need to put something down there to make your circuit, right? So you need a metal. And also can be the heat sink, especially if you are making an active circuit. You will have a lot of heat on it. It will become very hot, especially you are making a maybe PA. You have a bias current on it. You have a bias on it. So you have some metal make a heat sink. Can anyone tell people what is heat sink? Anyone? You can check it and tell people. Heat sink. 2 points. Anyone raise your hand? Metal can be a heat sink. No one? Yes. Louder. Yes. Okay. 2 points. Okay. Heat sink. This is a sink. Okay. And also can be a reflector element, because you have an antenna. If you have very special reflector antenna, your metal can be a reflector. Okay. So this is what metal do in our field, for the EM wave. And this is they are the equations and the table with resistivity and the room temperature. Okay, this is the resistivity. They have different numbers. You can check the table. The resistivity low will equals to R, which is the resistance times the area over the length. I think maybe you learned this before, R, about your resistance. And conductivity, sigma, is 1 over resistivity, 1 over low. They are very similar, okay? This is just like 1 divided by your resistivity will equals to conductivity. This is what that is. And this conductivity is the ratio between J and E. This is the equation we discuss again and again. Okay. What do we want? We want some material with the less resistivity. It's better. Okay, like what we usually use, copper, right? We use the copper as a material because the resistivity only 1.7 is very small. And if you have money, you can make it more. You want to better circuit, you use silver. Silver, okay, you know silver, right? And the people sometimes use gold. Why people use gold? It's only 2.3. Copper is better, but what is the good thing if you use gold to make your circuit? What's the difference? What is the property of gold? What is the good thing for gold? Can anyone answer? It costs much more, right? Raise your hand. Gold. Why you use gold to make a circuit and say it is good? What is a good thing? Raise your hand.
Low loss.
Low loss. No, I told you. Gold, the resistivity of gold is 2.3, but copper is 1.7, and the silver is 1.6. Understand? That's not the reason why people use gold. The people use gold is is resistance to the corruption. If you use copper or use silver, you touch your circuit will become very ugly because your hand has the sweat. It's a salty water on your hands. So if your circuit, I already tell you the answer, right? So the resistance of the corruption of gold. But the gold has actually good, as I said, does not easily corrupt. This is the answer. This is the answer. And it's expensive. But actually, silver is the best about resistivity. Silver is the best. But if you have something, if you have circuit made by silver, you need to be very careful. Don't touch it. Once you touch it, it will become black, ugly, and maybe they will change the property. Okay? So this is the conductivity, the table of conductivity for some of that. Remember, they have the unit. People forget the unit. Like 50% you report the conductivity equals 5.8 times 10 to the power 6, right? You forget a unit. Okay, and the temperature coefficient. This is, okay, just for your reference. If you actually, you see that? You have, for this one, you need to look at that. All the properties, all the numbers will change according to your temperature. Different temperature, different table. So I need to tell you, this is at the room temperature. You have this table, but this one will change according to different temperatures. So you have these equations, and if you change the temperature, you will have a different coefficient. This is the change of temperature. Okay, just for your reference. And also, skin effect is important for the conductor, especially when you are making a microstrip circuit, you use a conductor, or when you are making a circuit using waveguide. If you use a conductor, for example, waveguide, there is no material, there is no dielectric material, no insulator. There it is, it's like a rectangular hole, and they are all metals. Okay, you put a wave inside the waveguide. You use the waveguide. This is it's like a transmission line for your base system. Or radar, a very huge one, huge antenna. You use a waveguide, and all of that is a metal. If you do that, your electric field and magnetic field are inside this, right? Are inside this and transmit to another part. And we look at the rectangular metal. There are 4 metals, okay? Actually, if they are perfect conductors, all the E and the H fields are here. Okay, if it is perfect, but it is not. If it is not, your wave can penetrate inside the material, inside the conductor. Some of the wave will penetrate inside the conductor. Okay? Not only here. Okay, can anyone say which one? Well, which means wave can into the metal. Okay, not only in the air. This is metal. This is air. Okay, so your wave can be in also the metal. But how much wave will be in the metal? This is the skin depth. Okay, which is 1 over alpha. We will talk about alpha later. Alpha is if you someone I forgot which of you tell me that I think that's 预想 that when you give the wave equation, you give me this the form. It is the e plus time exponential minus gamma z, right? That's you, right? If you use gamma is a propagation constant, which has not only jk but also alpha. The k, we don't use k for the transmission line, we use beta. As I said, for TM wave, k is beta, right? So it's gamma equals to alpha plus j beta. This is attenuation because we are now talking about lossy. This is not a lossless case anymore. We are talking about if alpha is 1, if alpha is 0, this is a lossless case. If alpha equals to something, this is a lossy case. Okay? If there is a loss, we will have loss. We will have alpha. And this alpha is this alpha. Okay? And also this depth is equals to the square root of 2 over omega times mu and sigma. Sigma is conductivity. If sigma is very low, is 0, your skin depth is infinite. Okay? If your sigma is perfect, it's infinite, your skin depth is 0. Can you get it? Sigma is conductivity. For your material, if it is a conductor, perfect conductor, sigma is infinite, a huge number, and your skin depth is 0. Okay, and vice versa, you change that. Alright, so this is the skin effect we will discuss. If you talk about conductor, you will have a skin effect because your wave will be inside the conductor. But how deep it is, the skin depth. This is how deep your wave can be inside the conductor. You use this simple equation. Okay, and the dielectric. Okay, now is the most important thing we are trying to discuss. In the free space, we use this one, and in the linear material, linear media, we use this one. Why I say linear media? Because I'm telling you the most simple way to talk about the material. Actually, when we measure, you guys know I measure some of the epsilon R, right? I use some lines, or if you take the class for my for next semester, I will teach you how to measure epsilon R. Okay, but there are many ways to measure epsilon R. Your material. If this is a microstrip line, this is a conductor, This is the microstrip line, right? You try to know what is the epsilon for that. You make a circuit in this direction. You try to measure epsilon. The epsilon you measure, it is in this direction. But this is not the only way to measure epsilon. Epsilon will change according to different direction. If your material is not like on the PCB, it is a huge material like this big, and there is no conductor on it. Maybe you will have some problem to measure epsilon, and this epsilon is in this direction. There are many. Your world is just narrow. You know epsilon is just 4.3, that's it. But epsilon is depending on not only the temperature, but also the major direction, the major method, and also the frequency. Okay? You believe people tell you epsilon equal to 4.3. This is not accurate enough. There are many ways to give you the epsilon. And actually every time you have different epsilon. You have different board, they have different epsilon. Different machine, maybe you obtain different epsilon. Okay, we are talking about very accurate things about epsilon. So that's why we have the word. If this is a linear media on this material, then the same epsilon. We simplify the question. You use mu and epsilon, okay? So this is just a simple theory at the beginning. Okay, we already discussed this before. Okay. If you have a metal, this one is a metal. Okay. Metal is what? Why this is a metal? Because you have free charge in this material. All the charges is free. They can go anywhere. So that's metal. If this is a dielectric insulator, or FR4, or maybe Teflon, something glass, something insulator, we call dielectric. What's the difference between these two? Can anyone? What are the difference between metal and the dielectric about the charge? Okay, you can raise your hand if you already know the answer. Try to answer my question. You have current. Yeah, it's close. But good question. For the metal, you can have current. What does the current mean? What is current? If you see that closely, for both of them, they have charges, right? Positive and negative charges. Right? If you have the potential, voltage potentials on it, or you will say you will have an E field on it, apply an E field on it, okay? You give them a positive potential and negative potential on it. What will happen for the material, for the metal? How about the charges? They will move, right? Okay, you can earn 2 points. Okay? Because they are free. You apply. Okay? What happened for the dielectric? Anyone? Raise your hand. If this is a dielectric, nothing happened? Or something happened? The answer is either yes. Just raise your hand. I just try to say this story by my own, not just read my PowerPoint, because you will understand more if I derive this with you. Again and again, like what I did again and again. I didn't just read a book or I read my PowerPoint. I derived that from the beginning. Anyone? No? You just say that for the metal, the charge can move, right? It is free. So for the dielectric, what happened? Raise your hand. 2 points. No? Do you want to try? Huh? Charge can move. What's the difference between metal and dielectric? If you apply the E field of it, what happened? Charge won't move, right? But charge won't move. But look at that. They will change the direction because for the dielectric, which means for each small part of the, we call it dipole, minus positive, negative positive, they won't move directly like conductor, but they will turn at the same place. They will turn their direction. Okay? So if you apply the E field on a dielectric, all the dipoles will turn, and you will look at this one. After this is unpolarized, which means there is no E field on it. This is just a casual position. And for this one, if you apply the E field on it, all of them will change. Okay? They will turn in the same direction. Everyone will turn in the same direction. And after they turn, they change the direction because everyone change together. So they become a new vector, PE. Okay. PE is a result by everyone change the direction together. Okay? PE. So, what is the difference between if you have material and you don't have material? I will write down our D. If your wave is inside the air only, you use D equal epsilon 0 times E, right? If only air. But if there are something which comes from their turns from the material, there are different things, not only air. Those comes from those material, which is P, capital PE. Okay? So you can write down simply, you have different thing here. The why they are different is because you have material. No material, material. So P is only material. Okay? Okay? Can you close your eyes? You told me that you never close your eyes. Just only you should take a video. Okay. And for a P, you want to see a difference between this one and this one. You can redefine your PE will equals to your original epsilon 0 about the layer times the chi E times your also the E field. The only difference is you have one more variables chi E. You times chi E to epsilon 0 and times E, and this is our PE we're talking about. This is just another coefficient chi E. Okay? Should I get slower? Maybe you can check your textbook. Okay. So you can think about another coefficient times original one. That's it. Okay. You can to simplify this equation, epsilon E plus you will have something times original one. They are the same. Just time another one. Okay? Just I give you a number. They are different because we don't know this is, and actually this is very small because this is from the material. Alright?
那个是一瞬间出现的，还是会
Forever. Because yeah, forever. Because you have different material. Because you have different material. So they will turn all the material. If you apply the E field, they will turn and always turn. Okay. More mass. Because you times chi E, so you just write down equals to epsilon 0. So this is 1 plus chi E epsilon 0 epsilon E. Okay? It's nothing special. You just take the same part outside. Okay? And this one may be a complex, not just a real number. Then we will have another definition about epsilon, as I say, because this one can be a complex number. So you can write down epsilon equals to epsilon prime minus j epsilon double prime. Use another color. You work. This one is epsilon, right? This one equal epsilon prime minus j epsilon double prime, because this can be a complex number. And okay, let's try to connect something we already need. This one is epsilon r times epsilon 0. So this is what we learned before. We will only discuss only epsilon prime. Okay, the real part. Your 4.3 is this part. because they make the circuit, they use the FR4, epsilon R 4.3. It is this part only. Okay. Well, I told you epsilon equal epsilon R times epsilon 0. That is not accurate. They have more details. It is a complex number actually. Okay. This is a real part we discussed before, but you have an imaginary part as well. Okay. And why we have the imaginary part? There are some reasons. Because the damping of the vibrating dipole moment, the damping, the damping. And there are more details, and you have a loss. And this one is positive, so it's minus J, some positive value. Okay. Because I refer to a book talking about materials, they have more details, more than you think, right? So, loss tangent. Why I talk about that stuff? Because I want to tell you what is loss tangent. Everyone except maybe Ned, you never heard about loss tangent, right? No? No, but they hear about loss tangent. This is what is loss tangent. Okay. I have this equation I already give you. I use this equation, the second equation, the blue one, and I put everything back. Epsilon equals to epsilon prime minus J epsilon double prime. I put the J equals to sigma times E. I put everything here. So I can get everything together. Can you follow? For this term, they have the omega. For this term, no omega, right? This come from the second equation. Do I need to do that with you? Or you get it? Okay. You look very tired. This equation, for this part, okay, J omega D is epsilon E plus sigma E, alright? And epsilon equals to epsilon prime minus J epsilon double prime. And this one. So you can put J omega epsilon prime minus plus omega minus J is plus omega epsilon double prime plus sigma. Okay? We try to figure out which one is the real part, which one is the imaginary part. This one is the imaginary part, J, right? And for this part is the real part. We define loss tangent is the real part over the imaginary part. These two terms have something more complicated, like conductivity and epsilon double prime, which is like a vibration, right? A loss, media loss. So this one. Okay. And for this part is epsilon 0 times epsilon R. This is a real part. Okay. When you design your circuit, tell you loss tangent equals 0.017, it comes from these two terms. Right? you use 0.017, right? Loss tangent. Yeah, it's 0.02 and you say 0.017. This is. Okay, are we clear? Right? And then if you use RO board, it's 0.002. It's smaller. Right? It's a ratio of the real to the imaginary. If there is no sigma, just use the ratio of that. Okay, loss tangent. Why teach you to design a circuit first, then tell you, and you feel, oh, that's it, that's why. Loss tangent. If you never design a circuit, you don't know why this is important. Okay? Then you should design a circuit first. Try to design a circuit first. You will know why those are important. And finally, I'm telling you, you have most of the 90% of the information about epsilon R and the loss tangent. What you are using, why you are choosing this material to design your circuit, epsilon R and the loss tangent. Okay, you have 90% of knowledge already. If you understand what I'm talking about, you have, I think, enough information to do that. But of course, there are more accurate things. But those are the 90% of basic theories about materials. If you want to design a material, these two are most important, right? Of course, the thickness of board, but also I will ask you what is epsilon R, what is loss tangent. Then now you know. Okay, now you know. Okay, that's it for the our second class. Let me check if there is more. Okay, this is the table of material, the epsilon R, and the loss tangent at 25 degrees C. You have this table on your textbook appendix. In the appendix, you know the numbers, and see, this is a number at this frequency. So it's frequency dependent. All of them will change with frequency. Now you think about that before. You just give me a number that's not accurate. We can have a question. I just tell you the material, but I don't give you epsilon R and I don't give you loss tangent. You need to find your book to see this number. Like, oh, I have a material. It is a silicon. I use silicon to make a PCB and a printed circuit board circuit. Please decide. Check some number on it. And I say I will design for maybe 10 gigahertz, and you will use this number. Your epsilon R is 11.9. And your loss tangent will pick up this number. Okay? All right, let's take a break. And if you obtain any point, just come